Alright guys, this is going to be our final exam review to cover basically everything that we've learned this year into one video, and we're going to get to it. It's going to be a very long video, so take pauses and breaks in between and let's get started. So these are all the topics that I'm planning to cover and could possibly appear on your final exam. Okay, so we're gonna go through history of atoms first. So the history of atoms it's not too important, but it is important because you need to know or understand why the atomic model came to be as it is and the sequence of the discovery. Okay, so back then the first atomic theory was from Dalton. Okay, so Dalton, he thought the atom was just a round ball, and he named it the solid sphere model. That's our first atomic model. And then J.J. Thomson is the guy that put the magnet to the light that I showed you. So he discovered atoms must have positive and negative charges, but he didn't know where exactly the positive charge is. So that's why it's a huge positive sign in the center, or you can see positives all over the atomic model. So we call this the plum pudding model. Okay, and then the next one is Rutherford. He was shooting alpha particles towards gold foil, and then he discovered there is a nucleus. So remember when I used to throw the ping pong ball through the hoop? So right here, this is our first atomic theory with a nucleus. So he said all the positive protons are inside the nucleus. So that's why this is called the nuclear model. Then we have Bohr. Bohr discovered that there are different energy levels around the atom, and that's where the electrons lay on them. So we call them the planetary model because it kind of looks like planets is surrounding the sun. And then the last one is our current atomic model, is the electron cloud model, or the quantum model, okay, from Schrodinger. But this is beyond us. We don't really need to care about that one for now. We're going to study Bohr's model most. Okay, so right here, and also this guy is honorable mention because he came up with the word atoms, because atoms is basically just indivisible little particles. So Dalton used his name that was from thousands of years ago. Okay. Next one. Let's see. What is my next topic? Atomic theories. Here is periodic table. So let's look at our periodic table right here. Let's look at hydrogen, for example. Actually, let's do a different one. Sodium. Okay. So sodium, right here, this is our atomic number. Atomic number tells you the number of protons, and usually the number of protons is equal to the number of electrons. Okay, for normal atom. And then down here is our atomic mass number. This number is the total mass of an atom. And we use AMU for atomic mass. It's called atomic mass unit. Atomic mass unit. And for protons, it has a positive charge and it has approximately 1 AMU. And And for neutrons, it has no charge, and it has approximately 1 AMU. Okay, and electrons is the one that has negative charge, that has approximately 0 AMU. It does has a mass, but it's so light we can ignore it. So basically, the total mass is protons plus neutrons. So you can see right here, we got proton is 1, neutron is 1. So if the atomic mass number is 22.99, then we can round it to approximately 23. And we know the mass number is 23, but there's also 11 protons in there. So to find the number of neutrons, we have to subtract the number of protons in there. So for sodium, we have 11 protons because of that number. We also have 11 electrons, same thing because of that number. And then for neutrons, neutrons is equal to the mass number, or atomic mass number, subtract the number of protons. Okay, so 23 minus 11 equals 12. So we have 12 neutrons for sodium. And we have to use the mass number to calculate that one. What is my next topic? The next one is Bohr model. So for Bohr model, you can see on the different atoms, right here we have 1 circle, 2 circle, 3 circle, right? Those are the energy levels. So energy to understand Bohr model is best to also talk about the periodic table, how it is set up. So we can see right here, there's one across the period. So across the period or across the table is called the period. And just like your classes, you have 7 periods. So period 1, period 2, period 3, period 4, period 5, period 6 actually goes, you see this little empty block that gets moved down here. So period 6 actually goes like this, CS, BA, and then we go down to LA all the way to the end, and then come back here and continue. Okay, that's period 6. And then period 7 is the same thing. Let me use a different color. It goes from here, and then it goes down to AC all the way to the end, and then we'll come back to RF through it. So we got 7 different periods. And the number of period that the element is on will have the same number of energy levels. So for example, right here we have hydrogen. Hydrogen has a single energy level, just 1. And then if you look at lithium, it has 1, 2 rings or energy levels. Sodium has 1, 2, 3. Potassium has 1, 2, 3, 4. RB has 1, 2, 3, 4, 5. Okay, so looking across the table, same thing. Sodium has 3 energy levels. Mg also has 3 energy levels. Aluminum also have 3 energy levels. And phosphorus also have 3 energy levels. Going down the periodic table, it's called the groups. Okay, so we get group number 1, group number 2, group 3, 4, 5, 6, 7, 8, 9, 10, all the way to group number 18. So we'll have 18 groups. There's a lot of groups. And for there's also group A. Group A is 1, 2, 3, 4, 5, 6, 7, 8. And we skip the middle part, okay? The middle part is group B. So for group A, it's going to help us count the valence electrons. So right here, hydrogen will have exactly 1 valence electron. Be will have 2 valence electron, 1, 2. B will have 3 valence electron. So just looking at the periodic table, you can really quickly sketch out the structure of any element, okay? So let's say if I ask you to quickly draw calcium, you can either use the Bohr model, which is the ring. We got Ca with 1 circle, 2 circle, 3 circle, and 4 circle, because it has 4 energy levels, okay? And then on the outside, we only really care about the outside electrons. So on the outside, we have, for calcium, calcium is in group number 2. So let's look at this. It's in period number 1, 2, 3, 4. That's why it has 4 energy levels. 4 energy levels. And it's in group number 1, 2. So it has 1, 2 electrons on the outside, okay? And we call those electrons the valence electrons. Valence electrons are the electrons on the outside. So looking at the periodic table, you can quickly sketch out the Bohr model. And you can also use something that's way simpler. It's called the Lewis dot structure, or we can call it the electron dot diagram, okay? So calcium, you just write the symbol, and then we have 1, 2 dots. If you don't pair it, just put it, you can put the dots in any direction, okay? Doesn't really matter. Next one is the electron configurations. Okay, so for electron configurations, do you guys remember to complete let's just complete drawing calcium with all the electrons, all right? So to draw the complete calcium, we need to use this chart: 1s, 2s, 3s, 4s, 5s, and then 2p, 3p, 4p, 5p, 3d, 4d, 5d, 4f, 5f. So remember, all my s's have exactly 2 electrons. P's can hold 6 electrons. D orbitals can hold 10 electrons, and F orbitals can hold 14 electrons. All right, so it's gonna go like this. It has a diagonal rule. So you're going across 2, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So if you don't understand this or forget about this, you can also think about, I don't want to erase this, so let me use a different color instead. So you can look at the periodic table. So on the periodic table, over here we have highlighter. Over here we have our S block, including the HE is part of our S. That's our S. And then right here in the middle, this is our D block. That's our D block. And then over here we have our P block. Change it another color. This is our P block. And then on the bottom is our F block. So S has exactly 2. It can hold 2 elements. Right here, we got 2. So hydrogen is 1s1. Helium is 1s2. The 1 tells you the energy level, and then the S tells you the orbital, which is not that important. We just need to know the numbers on it. So this is on the first energy level, 1 dot. First energy level, 2 dots. So the Bohr model for H looks like this, 1 ring with 1 dot. And for helium, it looks like this, 1 ring with 2 dots because there is 1s2. Okay, and then for lithium, it has 3, right? So following this table or chart again, we have 1s. After 1s, it will be full with 2 electrons. So we have to move on to the next one, 2s. So that means that's on our second circle. So for something like lithium, it will have 1, 2 on the level 1 circles, and then on the level 2 circles, I'll have 1 dot. So 1 valence electron. Okay, so following this rule, let's let me erase all of this. That's too much. I'll just delete everything and redraw. So we have 1s, 2s, 3s, 2p, 3p, 3d. So it's going to follow this pattern: 1s, 2s, 2p, and 3s, 3p. So for my calcium right here, it has a total number of 20 electrons, right? So for 20 electrons, I will need to fill out this chart until I have 20 electrons. So let's draw this with the blue color. So for calcium, I have first is 1, 2. That's energy level 1s, okay? 1, 2. And then for energy level 2, I have 1, 2, 3, 4, 5, 6, 7, 8. So actually, it's better if I put this is a 1s1, 2s1, 2s2. This one will be 2p1, 2p2, 2p3, all the way to 2p6. Okay, so total on my second ring or energy level, I should have 8 dots. So 1, 2, 3, 4, 5, 6, 7, 8. Same thing for the next one. After 2s and 2p, I'm down to 3s now. So for 3s, I have 1, 3s, 2, and then come to 3p level all the way to 6. Okay, so for my third energy level, I also have 8 dots total. 1, 2, 3, 4, 5, 6, 7, 8. And lastly, where I need to get to calcium, this is my fourth circle. So let's use white color. So we got 4s1 and then 4s2. So for calcium, the energy level would be 4. So 4 circles, 1, 2, 3, and 4. And for the dots, I will have exactly, let me use a different color for dots. I have exactly 1 and 2 dots because it has 2 valence electrons on the period 4 with 4 energy levels, group 2. All right, so this is electron configuration, periodic table. Yeah. Next one is isotopes. So the reason why elements like the top few, let's say hydrogen right here, the reason why the mass number is not exactly 1, it has 1 point something, is because there is isotopes. So there is more than one type of the same element. So we have hydrogen 1, 1, hydrogen 1, 2, hydrogen 1, 3. Okay, so this is our isotope format. So on the top, this would be our atomic mass. The mass is on the top now, and then the bottom is going to be our atomic number. So you can see it's all the same element. That's why they all have the same number of atomic number, but their mass number is different. Again, this number is the number of protons, right? So protons, and protons don't change. They all have the same number of protons. And remember our AMU for protons, neutrons, and electrons. So protons is approximately 1, neutron is approximately 1, electron is approximately 0. So if protons are not changing, that means the neutrons are changing. So basically, isotopes are elements with different number of neutrons. That's it. That's what isotopes are, okay? And for hydrogen, 99% of hydrogen is just hydrogen 1, and then there's 1% of hydrogen 2. So if you do the calculation for the percentage, so 99% times 1 plus 1% times 2, the atomic mass. Let me do the math. I think I did this right. So with a calculator, 0.99 times 1 equals 0.99. And then 0.01 times 2 is 0.02 plus 0.99 equals 1.01. So this is the rough estimate for atomic mass of hydrogen. Okay. So same thing, if you do the same thing for the other elements, that's why their mass numbers have decimals, is because of isotopes. All right. So so there's the 3 main particles. We have protons that are positively charged, neutrons, no charge, electrons, negatively charged. So protons, they do not change. Do not change. There is no change in protons ever. If it changes, then the whole element will be different. So that's nuclear reaction. But we don't, so if the element has 3 protons, it will always be lithium. And lithium will only have 3 protons. If the number of protons change, it's not the same element, okay? The neutrons can change. So when neutrons change, we call them isotopes. And then electrons can also change. We call those ions. So the only thing that doesn't change is the number of protons. So right here, protons don't change, neutrons can change, electrons can change. So that's the 3 rules to remember. So for ions, we'll have to talk about the octet rule, okay? So the octet rule is basically the rule of 8. So just remember 8 balls. So, or oct, for octopus, it has 8 legs. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, helium is a special one. Helium only have 2. Remember our, let me use this green color. Helium only has 2 because hydrogen is 1s1. And then helium is 1s2. So that's a special one. Everything else below helium is 8. Okay, so remember these numbers. These are, we already talked about this. These are our group A for valence electrons. Okay, valence electrons. So for lithium, it has 1 dot. And for beryllium, this one, it has 2 dot. Let me clear my board first and rewrite this. So lithium has 1 dot, beryllium has 2 dot. Next one is boron. Boron has 3 dot, 1, 2, 3. Carbon has 4 dots, 1, 2, 3, 4. Nitrogen have 5, 1, 2, 3, 4, 5. Oxygen has 6, 4, 5, 1, 2, 3, 4, 5, 6. And then fluorine has 7. Let me erase this little dot. Fluorine has 1, 2, 3, 4, 5, 6, 7. And then neon over here, I'll put it, I'm running out of space. So I'll put neon right here. It has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so basically the octet rule tells us that elements will be happy when they are full. Okay, so going back to electron configurations, remember the p orbital over here. So this is the p orbital. So if it's p1 or p2 or p3, 4, 5, they're all unhappy. They're not complete. So they want to be complete like the noble gases. So noble gases are happy because their electron orbitals or electron shells are complete. Okay, so octet rule basically tells us 8 is our happy number, and there's also a duet rule. So the rule of 2 for only hydrogen and helium. But we don't really care about the duet rule because it's only 2. You can remember that. But octet rule, all the other elements prefer to have 8 valence electrons. So someone like lithium over here, they would have a hard time to gain more electrons. It would need to gain 1, 2, 3, 4, 5, 6, 7 electrons to be happy, and that's too much work. So again, nature prefers to use the lowest amount of energy to be happy. So what lithium would prefer to do is actually lose that 1 dot and move backwards on the periodic table. So it's going to go all the way to helium instead. So it's going to go from element number 3 back to 2. And by losing that 1 valence electron, it will be happy because now instead of, let's see, delete this. So now instead of having 2 rings, so lithium has 2 rings, Li, 1, 2. Instead of having 2 rings with 1 valence electron, lithium will get rid of that electron. And this whole energy level is gone. So now it would have like that. It will look like this. So just like a noble gas, helium. That's what helium looks like. And helium is happy. So lithium can be happy just like helium, okay, by losing that 1 dot. So that's why elements form ions, because they want to lose their electrons so they can be happy. So something like sodium works exactly the same. So sodium has 3 different rings. We have Na. It has 1, 2, 3. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, and then 1 dot. Okay, so sodium is not happy. What is happy, that's right next to sodium. So it kind of looks like sodium is down here, but sodium and neon over here is actually connected. So right after neon it comes to sodium. Okay, so what sodium wants to achieve is the electron configuration of neon. So sodium will get rid of this electron and look just like neon. So let me draw out neon. It has 1, 2, and all the shells are complete with 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So by losing that 1 dot, sodium will be happy. So that's why elements form ions. So when sodium or lithium loses one electron, what happens is lithium with one less electron, it will have 2 electrons, okay? That means it has 2 negative charges. But remember, it still has 2 protons, 2 positive charges. 3 protons. It still has 3 protons, 3 positive charges. So if we draw it out, it will have 1, 2 negatives and 1, 2, 3 positives. So positive and negative, they will cancel out. Positive and negative, they will cancel out. So by becoming happy, lithium will have to hold on to a positive 1 charge. And we call those cations because the plus charge that's on it looks like a T in the cat, okay? Or you can think of cats have paws, so it's positively charged. So cations. The second type of ions that we learned is anions. So anions have negative charge. Cations have positive charge. So cations have positive charge not because it gained a electron. It's because it lost an electron and has a positive charge. Anions is the opposite. So for example, fluorine, F. F has 1, 2, 3, 4, 5, 6, 7 dots, okay? So for fluorine to be happy, it doesn't want to lose all 7 dots. That's also too much work. So the fastest way for fluorine to be happy is actually to gain 1 more dot, okay? So gain 1 more dot and become neon. So by gaining an extra electron, fluorine will have 10 electrons and only 9 protons. So if you forgot how to determine the number of protons, again, the atomic number is 9, so it has 9 protons, okay? So again, we have an extra electron over here. So for fluorine, it will have an extra negative charge because electrons are negatively charged. All the other 9 gets canceled out, so it has a -2. So same rule applies. If we have oxygen, oxygen has 1, 2, 3, 4, 5, 6. If it gains 2 dots, that means it will have 2 extra electrons or 2 extra negative charge. So oxygen will have a -2 charge. Same thing for beryllium. Let's do boron. Same thing for boron. Boron likes to gain how many more or lose how many? So boron has 3 valence electrons. So it would be faster to go backwards on the periodic table. So go from boron to beryllium to lithium back to helium. So their goal is to land on the noble gas part. Okay, so it's just which way is faster. So for boron to go lose, it will go from 1, 2, 3 steps. To gain, it will have to go 1, 2, 3, 4, 5 steps. So again, the shorter way is the best way. So instead of gaining 5 more, it would prefer to lose those 3. Okay, so borons will lose those 3 dots. That means it will have 3 extra protons. That's 3 extra positive charges. So boron will look like this. Boron will look like B with a +3 because it lost all their dots. Okay, so this is the ions. So after talking about ions, it perfectly leads into ionic bonding. So ionic bonding. So why do ions form? Is because elements wants to be happy, but they can't just give away electrons to nothing or take electrons from nothing. They have to give and take from each other, okay? That's why they form bonds. So lithium and fluorine will be perfect friends because lithium wants to lose that dot and fluorine prefers to gain a dot, right? An electron. So fluorine has 1, 2, 3, 4, 5, 6, 7. So by lithium wants to get rid of this, fluorine wants to take it. And there you go. Transfer. Electron is transferred in this case, and they will each become an ion. So we call this ionic bonding. So LF is, no, LIF is an ionic bond. So ionic bonds, another characteristic to remember is often a metal plus a nonmetal. Okay, so if you forget metal and nonmetal, let's go over this again. So first one is alkali metals. So lithium, sodium, potassium, all that stuff. Alkali metals does not include hydrogen. Okay, hydrogen is a gas. It's not metal. It's nonmetal. You can see the color is green. Alkaline earth metal right here, and then transition metals, post-transition metals, metalloid. So basically, let's draw this. Basically from over here, it's all metal. So we have a lot more metals than non-metals, okay? And everything else is just non-metals. So we got hydrogen, carbon, all of these stuff are non-metals, okay? And actually there is a special border between them, and those are the metalloid. Metalloid is boron, silicon, germanium over here. So metalloid is in between metal and non-metal. They're half and half. So they're not technically metals or non-metals. So they're the special ones. So ionic bonds. Let's remember this. Ionic bonds. Bonds are usually between metal plus non-metals. Okay, but sometimes they can have non-metal plus non-metal. We will have to bring in polyatomic ions, which is just ions that formed a bond between each other and still have a positive or negative charge. So I think let me look for one example. Polyatomic ionic bond. So something like NH4 will have a positive 1 charge, and N is nonmetal, H is nonmetal, and by having that positive charge, I can bond with something like fluorine with a negative charge, right? So they can bond together and still have no metals in there, but those are special. The more common ones are between a metal plus a non-metal. That's for ionic, okay? So the fast way for us to remember is ionics are metal plus non-metal. And then for the other combinations would be non-metal plus non-metal, right? So this would be covalent. And then the last type of combination is metal plus metal. This one is metallic. Okay, so metallic is basically forms some type of alloy. So ALLOY. Alloy is basically just a mixture of metals, okay? And metallic bonds, they will have a sea of electron. So let's look at the characteristics of the elements again. So for example, we got copper, Cu, and iron, Fe. Okay, before we talk about metallic bonds, let's talk about the element symbols. So I kind of went too fast earlier. So the reason why some elements does not have their symbol and name match is because they're Latin names or ancient names. Okay, so metals like copper or iron or gold, they have been discovered thousands of years ago. This is before alchemy or chemistry was a thing. So people already have name for them. So for example, sodium, why is it not SO? It's because the ancient name for sodium, or Na, is called natrium. Okay, or tin, Sn, is Stannum. Okay, and then same thing for gold and silver, like we talked about in class. Ag is, I think, is Argentum, and then Au is Aurum. So it's their Latin root words. Okay, so also you can see there's a lot of elements with 2 letters. Some elements have 1 single letters. So anytime you see an uppercase letter, that's a single element. Okay, so B is 1 element, or N is 1 element, H is 1 element, but if I lowercase 1 letter on the back, it will be a whole different element. So for example, let me circle these. So we have CO and C and O. This is carbon, this is oxygen, this is cobalt. Completely 3 different things, okay? So carbon, oxygen, cobalt. So lower letter, okay? So if you see lowercase letters behind a uppercase letter, then they're always together. Same thing with N, nitrogen, H, hydrogen, and then there's an element called NH somewhere. I forgot where it is. Where is it? Oh, right here, NH. So completely different things, okay? And also this one, Cl, a lot of people confuse chlorine with carbon and iodine, but I guess that's a valid confusion because it does look like 2 uppercase letters, but just be careful with carbon, iodine, and chlorine, okay? So if chlorine is bonded with some kind of metal, then it's an ionic bond. It's not carbon and iodine. So just be careful with that. All right, let's go back to metallic bonds. Metallic bonds are bonds between metals only, okay? So for example, we have iron, Fe. This is why I got sidetracked. Is because of the Fe, different symbol. Okay, next one we have something like gold, Au. If we mix them together, they become an alloy. So how exactly do they mix? Is because remember all the elements over here have less than 3 valence electrons, so they prefer to lose their electrons. So they prefer to lose their electrons than gaining their electrons. Give me 1 second. So that is why all of these elements, instead of partnering up or bonding together, they would all share or donate their electrons. So lithium, lithium. Let's mix it with some tin, SN. Actually, lithium and tin, I don't think they bond. That we can mix sodium and potassium. That's like very, very explosive. NaK, NaK, Na, K, Na, stuff like that. So both Na and K will donate their electron out because nobody is there to take the electron. So what happens is they will end up with a sea of electrons. And remember, they have charges. When they lose their electron, they all also have a positive 1 charge. So sodium and potassium, they're both very, very positive after losing that electron. And then the sea of electron is very, very negative. So that acts like a glue to hold everything together. Okay, so that's why metals are malleable. They can change their shape without breaking. So it's not like a crystal structure, right? So that's why they can bend and be hammered without being shattered. But non-metals, on the other hand, they're usually very brittle, okay? So that's why they have those characteristics. So let's look, that's pretty much it about metallic bond. Metallic bond is very simple, just a sea of electrons. For covalent bonds, it only happens between nonmetals. Okay. So how come metals cannot participate in this? That's because covalent bond, they work by sharing electrons. Share electrons. Okay. So think of something like lithium. Lithium, it only has 1 electron to share, and even if it shares with some random element, it will only have 2 electrons on the outside circle, and it's not happy. Remember, our happy number is 8, and having 2 is not complete. So lithium cannot be happy by sharing. Same thing with calcium. It has 2. It only has 2 dots to share. Calcium, even if it shares 2 with somebody else, it will only end up with 4. So that's 4 valence electrons, not happy, okay? But nonmetals, on the other hand, they're usually over here. They have 5, 6, or 7 valence electrons, so they can afford to share. So for example, oxygen. Oxygen has 6 dots, 1, 2, 3, 4, 5, 6, and let's bond it with itself, another oxygen. So we can bond it with another oxygen, and by sharing, let's do a blue color. They will share those 2 dots, okay? So this oxygen right here will have 1, 2, 3, 4, 5, 6, 7, 8 dots. Same thing on the other side. 1, 2, 3, 4, 5, 6, 7, 8 dots. So both oxygens are happy. They achieve the octet rule, and by sharing without losing or gaining any electrons, they just share. Okay, so the pure oxygen that we breathe in is usually O2. Same thing for the other gases. They prefer to be in twos. So N2, O2, F2, Cl2, H2, because they all can share electron by themselves. So pure gases will be in twos. That's pretty much it for. Oh, let's actually share something different. Let's share nitrogen with hydrogen. Okay, so hydrogen only has 1 dot to share, and it will be happy with 2 dots, right? Nitrogen has 1, 2, 3, 4, 5 dots to share, and it only wants 8 dots. So how many times does nitrogen want to share? 3, because it needs 3 more. So let's bring 3 hydrogens to bond with it. So we have H1, H2, H3, and by sharing those electrons, each hydrogen will have 2 dots, and the nitrogen will have 8 dots. So they're all happy. This is NH3. Okay. Same thing works for carbon and oxygen. So there's also double bonds. So for example, I just did a double bond, oxygen, and oxygen is a double bond. There's also a triple bond, nitrogen plus nitrogen would be a triple bond. So yeah, that's pretty much it about bonding. So bonding is ionics or transfer electrons between ions. Okay, transfer electrons between ions. Covalents will share electrons, and only nonmetals have enough electrons to share. The metals, they don't have enough electrons to share. And the metallic bonds, they all want to share or give away their electrons, and nobody is there to take the electrons. So metallic, they all form a sea of electrons. So that's the 3 types of bonding that we will learn and master for high school. Okay, there's more types of bonding, but it gets complicated. Oh, and also talking about ionic bonds, also something like think of atomic sizes. Okay, so element, that's actually, I'm not going to test you about atomic radius or atomic or ionization energy or electronegativity. If I cover those, it will make the video too long. So I must skip this for now. If you're interested or if you forgot, you can go YouTube or Google it. But I will skip those 3, okay? Next one, we have chemical naming. So all the names, when they bond together, they are called, they always end with IDEs. So IDE. So for example, LIF. This is lithium fluoride. Oh shoot. FLUORIDE, fluoride. So the ending goes from fluorine to fluoride. Okay. Same thing. Sodium chloride, potassium bromide. So, or magnesium oxide or calcium sulfide is all IDE ending. Okay. So for a lot of the ionic bonds, that's it. This is your name for the chemicals. Really simple. If it has polyatomic ions, it can get a little more complicated with oxygen containing polyatomic ions. We will have to add ITE and ATEs, but I won't test you on this. For covalent bonds, you will have to specify the specific amount. Remember this right here. Carbon and oxygen, they both can bond together, but they can actually create quite a few combinations. Okay, so it can become CO, carbon monoxide, CO2, carbon dioxide, or CO3, carbonate. So for example, right here, CO, that's carbon, and then 1 oxygen, we add mono oxide. So MONOXIDE, carbon monoxide. And then if we have CO2, that's the very famous dioxide, D. Okay, This is not trioxide because at this point it becomes an ion, polyatomic ion with oxygen. So we have to add an ATE for it. Okay, so naming gets a little confusing, but just remember if something contains mono, di, tri, tetra, penta, hexa, hepta, octo, nona, and deca. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in chemistry. All right. Other than that, I won't really test you on chemical naming. You just have to realize what they are when you see these names, because later on in Unit 5 with stoichiometry, there's a few reading problem with chemical names in there, and you have to know what you're dealing with. Next unit covers the different types of reactions. Okay, so from here on, we don't really need the periodic table. So let me use a blank sheet. So over here. So in this unit, we cover the types, different types, types of is lagging of. Let me redo this. Pen types of reactions. Okay, so the different types of reactions contains stuff like number 1, combination. This is A plus B gives us AB. Another name for this is synthesis. Exactly the same reaction, okay? It's just combining. That's why it's combination. Number 2 is decomp. Decomposition reaction is basically the reverse of combination. Is AB breaks down into A plus B. Okay, it doesn't even have to be AB. It can be more. It can be ABC or ABCD, and then it breaks apart into A plus BC. Okay, so as long as breaking apart or A plus B plus C, whatever, doesn't matter. If they're breaking apart, that's decomposition. If they're combining, it's composition. I mean, combination. Okay. A real life example would be like this one. Combination Na plus Cl2 becomes NaCl. And this one is NaCl breaks apart into Na plus Cl2. Remember, the gases, they prefer to be in twos because they share electrons. Okay. Sharing. That this is a covalent bond. And then reaction type number 3 is combustion. This one is pretty unique because you need a fuel plus oxygen to burn. You always need oxygen, and it's always going to generate water and CO2. Okay, it's not just water and CO2. When stuff burns, it creates all kind of nasty stuff. But water and CO2 will always be there. And then reaction number 4 is single. Actually, we can combine 4 and 5 together. So 4 and 5 is single and double. 4 plus 5, single and double replacement. or displacement. Same reaction. So the single one is like this. A plus BC gives us AC plus B. So A replaced B, and B gets kicked off to be alone. So single replacement. One element gets replaced. And then for double, it would be something like AB plus, let's use 1 and 2 instead of numbers, instead of letters. So it's A will combine with 2, A2 plus 1B. 1 will combine with B. Okay, so two things will switch places. So this is a single, this is a double. Single replacement, double replacement. Okay, that's the 5 different types of reactions. Why does it happen? It's actually because the reactivity. But again, I'm not going into electronegativity. After that, we have indications of chemical reactions. So what are the 5 indicators of chemical reactions? So remember, actually there's 6. We did 2 labs on this. There's like different parts to it. So again, if there's a temperature change, then a chemical reaction has happened. Okay. Another one is if you smell something, a new odor is being produced, then that's a chemical reaction. You know a chemical reaction has happened. So if you cook a steak or you burn a toast or something like that, you get a new smell, a chemical reaction has occurred. 3, you get new color change, right? So when you burn a toast, you not only get a smell, you also get a new color. So color change. And then step number 4 is what's another one? Gas formation. So whenever there's new bubbles or gas being made, then that means there's a chemical reaction happening. And number 5 is color change, temperature change, odor, gas, precipitation. So precipitation is basically solids forming in liquid. Okay, so an easy experiment for you to do at home is mix Coke with milk, and then the acid will turn the lactose in the milk into like chunks. So that's precipitation. You get something solid with 2 liquid mixing. Okay. Number 6, we also did a lab where it started to glow. So chemiluminescence. So lumi is also like glowing. I guess that's like a color change. So same thing. Okay. So 5 indicators of chemical reactions. And then next one, we have balancing chemical equations. So balancing is the annoying one. Actually, it's not even that bad comparing to stoichiometry. So balancing. How come it's not writing? Okay, balancing, let's try this one. CH4 plus O2 makes CO2 plus H2O. So we have our fuel, our oxygen, CO2 and water is being made. This is a combustion reaction. Okay. But let's see how if you remember how to balance. So under this arrow right here, draw a line. You can do C, H, and O. Try to match them. Okay, whatever you have right here, do the same letter. That way even though it's a C and an O next, doesn't matter. Try to match the letters so you don't get confused, because a lot of people confuse themselves because the way they write. So after you do that, you can start counting the elements on each side. So for this one, you're only counting this side. And then for the other side, you're only counting this side. There's two different sides, okay? So don't count different sides. So let's do one. We have carbon, there's 1. Hydrogen, there's 4. Oxygen, there's 2. On this side, I have 1 carbon. How many oxygens? We have O2 here, and there's another O right here. So it's technically 3 oxygens, okay? And then H, there's only 2. So that's the counting part. Now let's do some balancing. So we have carbon 1 and 1, that's good. Hydrogen, I have 2 and 4. So since you always want to, so if you have 2 oxygen at 2 different places, you always balance that those ones last and do hydrogen first. So H2 multiplied by 2, this 2 will distribute into H2 and make it a 4. 2 times O, that's going to be O2, plus this O2 is actually O4. And then to make this side O2 into a 4, I need to multiply it by 2. So again, you can only add coefficients, okay? So the coefficients are the big numbers in the front. So 2 times O2 is O4. And that's pretty much it. Everything is balanced. We have 4 hydrogens on both sides, and then 4 oxygens on both sides. So after you're done balancing, you can add a 1 in front of the elements that you didn't change their coefficient. So the answer for this one is 1, 2, 1, 2. Okay, so that's how we balance chemical reactions. Also, when you're counting something, for example, like Fe, Fe2, SO4, 3. This 3 only applies to whatever is inside the parentheses, okay? And this 4 and 2 only applies to whatever it is after. So this 4 is only after O, so you only care about the oxygen. So right here I have Fe2, S. There's one S. There's no other number behind S, but remember there's a parentheses right here, and there's 3. So 3 times 1S is 3S, and 3 times O4 is O12. Okay? And then if you add a coefficient in the front, let's say you add a 2 in the front, this 2 will distribute into everything. So basically everything times 2. So Fe will become 4, and then S will become 6, and then O will become 24. Okay. Next one, we get into Unit 5, stoichiometry. So for stoichiometry, this is the most difficult unit in chemistry. So if you're struggling, you have another chance here to focus and pay attention. So remember our mole map. We have mole A and then mole B. The reason why we have 2 different mole is because when we are balancing or calculating between 2 different substances, you have A and B. Don't mix them. They're 2 different things, okay? It's kind of like different currencies. If you're using pesos or Chinese dollars, right? Yuan with US dollars, dollar. We got 2 different countries, two different currencies. That's mole A and mole B. They do not equal to each other. There is a exchange rate, and that rate is what we call molar ratio. Okay, molar ratio is basically the coefficients that we just did in front of a balanced chemical equation. Next one, within each mole, there's also specifications for different stuff. So right here we can have particles. Over here we have the mass, atomic mass or molar mass, and then we have liters. So liters is always 22.4. Particles is always the Avogadro's number, 6.02 times 10 to the 23rd power. Then molar mass is different depending on which type of chemical it is. So you got to check on the periodic table in grams. Okay. Same thing on the other side, particles. So again, particles, don't confuse yourself. There's multiple type of particles. We got molecules. We got formula units. We have what else? Atoms. That's single elements, right? So those are all part of particles. And then we have molar mass again in grams, and then liters, 22.4 L. So basically this is our mole map. Okay, so let me actually take a screenshot of this so I don't lose this drawing. New. There you go. Okay. I will be using the screenshot later. But for now, let's try one problem together. So this one, consider the balanced equation for the production of ammonia. So we got N2 plus 3H2 making 2NH3. So it's pre-balanced for you and we just have to calculate it. So question is, how many moles of hydrogen, H2 question mark, are required to produce 4.5 mole of ammonia, NH3. Okay, so right here we have two different substances. We have mole A and mole B. Okay, so we have two different moles here. That's why if we look back at our mole map right here, we're going across from mole A to mole B, and we have to use the molar ratio. That's a one step. Okay, we're not converting between grams, liters, or particles. We're just going from mole A to mole B. So this is a pretty easy one. So I'm going to start. You always start with your given. Okay, so always start with given. So we know there is 4.5 mole of NH3 times, and we're trying to convert it into number of mole for H2. Okay, so this is my setup. After you get to this point, we can finish setting this up. We're gonna bring mole NH3 down here. So because we have to cancel it out, that's why we bring mole NH3 down here. So mole NH3. And the reason why we do this is so later at the calculations, all the NH3 will be able to cancel each other out like that. Okay, but for now, let's fill in the numbers for these two. So what number do I put here? You have to make sure they equal to each other. Mole H2 has to equal to mole NH3. So basically we're not changing anything by number. This is technically is equal to 1. Remember, anything that is the same divided by itself is equal to 1. So you have 5 divided by 5, it will equal to 1, right? So I'm not changing this number 4.5, I'm just converting it. So how can we make sure they're equal? So this is where we use the balanced equation. So for H2, the coefficient is 3. So for every 3 mole of H2, I should be able to make 2 moles of NH3. So the ratio is going to be 3 to 2. Okay? And then using a calculator, let me pull up my calculator. I will have 4.5 times 3 divided by 2 equals 6.75. So the answer for this one is equal to, oh, I'm out of space, is equal to 6.75 mole H2, okay? Because mole NH3 have been canceled out. This unit is gone, so it's just mole H2. And to put this in the calculator, you have to do 4.5 times 3 divided by 2. Everything on the top will get multiplied, everything on the bottom will get divided. And you always start with the first number, okay? That's how we do these type of questions. So let's do another 3-step example. So this one is, if you have 5 grams of H2, so this time, instead of giving you the mole number, it's telling you the gram number. So 5 grams of H2 and also 10 grams of O2 are mixed. How much water can be produced? Oh, okay. So this one, we have to use limiting reactant because we need to figure out which one is going to run out first. Okay. So first of all, gram and gram does not convert directly. So if we look at our map, let me bring my map back. So if we look at our map right here, to go from grams, let me use a different color. If I go from grams to grams over here, they don't directly convert. So I need to actually convert from grams to mole A, and then this grams to mole B, and then compare mole A and B, okay? So let's do that first. Hydrogen, we have 5 grams. Oxygen will have 10 grams, okay? So remember, our mass for hydrogen is equal to 1. Our mass for oxygen is equal to 16. And there's H2, so 1 times 2. And then O2 is 16 times 2 equals 2 grams per mole. This one is 32 grams per mole, okay? So let's do the calculation. We have 5 grams of H2 times mole H2, and then we'll get to mole O2, and then to actually, yeah, grams O2. So I can just straight calculate for the grams of oxygen I need. So the next step is to bring all the diagonal units right below. Okay, so over here is going to be grams H2, down here is going to be mole H2, down here is going to be mole O2. And after setting up the conversion, I can plug in the numbers. Okay, so the numbers for this one is every 1 mole is equal to 2 grams. Every 1 mole of oxygen is equal to 32 grams. And then the molar ratio between these two is H is 1, H is 2, and O is 1. Let's do the calculation. We have 5 times 1 times 1 times 32. So anything times 1 or divided by 1 is the same. Cancel them out. Grams divided by that, mole. So we have 5 times 32 divided by 2 divided by 2 equals, calculator, 5 times 32 divided by 2 divided by 2 equals 40. Okay. Equals 40 grams of O2. So that means for every 5 grams of H2, I will need 40 grams of O2, which I only have 10 grams of oxygen. That means I'm going to run out of oxygen first. So I had to use oxygen to do my next part calculation. Okay. My goal is to find out how much water I can make. So now I know I'm going to run out of oxygen. So I'm going to use oxygen as my next step. So I have 10 grams of O2 times, I have to go from grams to mole O2 first, and then from mole to mole H2O, and then from mole H2O to grams H2O. So again, H and then 2O1, H2O water, H is 2 and then O is 16, so 18 grams per 1 mole of H2O. Down here, bring the diagonal units. Every 1 mole of O2 is 16 times 2, 32 grams. And then down here is mole O2, the mole to mole. Whenever you see mole to mole, you have to use the coefficients. So H2O is 2, oxygen is 1, so 2 to 1 ratio. Now you can cancel out the repeating units. And we have 10 times 2 times 18 divided by 32. Calculator. 10 times 2 times 18 divided by 32 equals 11.25 grams of H2O. Okay, so basically what we just did is we found out if given 5 grams of hydrogen gas and also 10 grams of oxygen gas, we are only able to make 11.25 grams of water because we're going to run out of oxygen, even though we have leftover hydrogen gas. But oxygen is our limiting reactant. Okay? And that's pretty much it for stoichiometry. I'm going to skip Avogadro's number because it can look intimidating and it might take too much time from your calculations. So we're going to skip that. And then the last part is thermochemistry. Thermochemistry, I've already made a video. My throat is hurting right now, so I'm going to end this video and I cannot talk anymore. So just go to your Google Classroom here. Go to classwork under under finals, and unit 6. This one is the thermal one. I know I was writing on paper, and not like this type of recording. But yeah, you just watch that video and it should help. Okay. Hopefully you guys do good on the final exam and pass my class with really good grades. See you guys in class.